Hello and welcome to the DMM DVP series integrated wheel drive load calculation tutorial for AGVs and AMR robots. So before we begin, I just wanted to mention that the reason why we put together this video is because a lot of our customers have been asking us about the difficulty of calculating load versus motor size and gearbox reducer sizes and wheel diameter, obviously, for AGV and AMR applications. Typically, mechanical numbers for regular mechanisms like ball screws and linear and rotary travel is quite straightforward, but for AGV applications, it can be a little bit complicated, so we sort of just put all of the calculation methods in one comprehensive video. Before we begin, I just want to give a quick overview of the DVP product construction. We have this main steel frame here that's used to hold everything together, including the heat sink and all the bolting points. So the DVP has, for convenience, we have four vertical mounting points here, and we also have 4 horizontal mounting points, which you can't see, to bolt the product onto your robot frame, which makes it very convenient. So you can do a vertical or horizontal mounting. In addition, on the front, obviously, you have the wheels, which comes in different diameter options here. We have the status LED strip, which you can easily see from the outside to check the status of the product itself. And on the back, we have a couple of straightforward connectors, like the USB connector and the brake and STO connector, and the IO connector for the pulse analog control and the alarms and enables and the homing and those types of signals. And obviously, we have the main DC 24 to 100 volts DC power input connector. And we also have the communication connectors for CAN, Modbus TCP, Ethernet IP, or EtherCAT, or whichever option that you choose. The internal construction of the product looks like this. So we have the wheel in the front, obviously, and a couple of mechanicals to hold everything together, with the precision planetary gearbox that we use for motion control applications bolted into the middle. And we also have the servo motor in the back with the our standard DMM encoder. The motor and the gearbox are all standard DMM product lines, so we are able to keep this product, keep and manufacture and sell this product at very good lead times and pricing as well. And we have a customized DC high power servo drive module along the side here, which are all the IOs are connected into. So before we begin, just a quick outline of the DVP product line. So we have the 75 millimeter. The main difference is going to be the wheel diameter, which you have a choice of 75 millimeter, 100 millimeter, or 160 millimeter wheel diameter options. With all the products are 24 to 100 volts DC input with different motor sizes selectable in between each sizes. And we also have 1-stage or 2-stage gearbox reducers available, and all the specs for the speed and the payload are shown as on the screen. So let's start with our sample calculation. So before we start with the sample calculation, we sort of have to define a couple of different variables here as shown on the screen. These are the main variables that we're sort of going to need to know for the calculation. The first one is going to be the total vehicle mass, obviously, which is the mass of the vehicle itself, the entire vehicle, plus whatever payload is on top. The wheel outer diameter, which is the diameter of the driving wheels, which is the diameter of the DVP product wheel diameter. And we also need to know the reduction ratio of the system, and the gearbox inertia, which is the inertia of the reducer of the gearbox itself. The mass of each wheel we need to know, and the number of drive wheels that we need to know, or we can select, as we run these numbers, as you will see later on. And the rolling friction between the wheel and the surface that it is traveling on, along with the torque transfer efficiency. This is how much torque is transferred from the motor onto the ground itself on the mechanism. And a torque safety factor, which is sort of needed in all motion control applications. And the rated speed, how fast you want the robot to be moving during regular operation, and the acceleration time, which is how long do you want the robot to take to go from 0 to the rated speed of operation. So let's just do a sample example calculation here as shown on the screen. So we're going to take a total vehicle mass of 1,500 kilograms, which is the mass of the vehicle, including payload, of course. We're going to use a 100 millimeter diameter wheel option with a 20 to 1 reduction gearbox and here is the the inertia of the gearbox as shown on the screen, and here's the mass of the wheel. And we're gonna run this system with 2 drive wheels on the robot with a 0.03 rolling friction, which is the standard, with 80% torque transfer efficiency, which is pretty standard. The gearbox itself has a loss of about, like 5% or so, typically speaking, and through mechanical transmission or whatever, there's always losses, so 80% is usually a pretty good estimate. With a torque safety factor of 1.5, which is pretty conservative for AGV applications. We want a rated speed of 60 meters per minute, so it travels 60 meters in 1 minute as the rated operating speed of the robot, with an acceleration time of 1 second. So it goes from 0 to 60 meters per minute in 1 second of acceleration. So a couple of these are just example parameters, of course. The rolling friction and the torque transfer efficiency and the torque safety factor, typically you want to just leave it at 0.03, 80%, and 1.5. All of the other parameters are sort of freely selectable depending on the application requirements. So actually, before we move on, I want to show you how we select the inertia of the gearbox plus the mass of the driving wheel. Obviously, we've selected a DVP 100 millimeter diameter wheel with a 20-to-1 reduction gearbox. So if you look at this chart here, we have a DVP 100 and a 20-to-1 reduction is going to be a 2-stage gearbox, which uses the DPGS product line. And if we go into the DPGS gearbox manual, you can look up the inertia of the gearbox on the manual itself as a 80 millimeter gearbox with a 20-to-1 2-stage reduction has an inertia of 0.44 kilograms centimeter squared. And also the mass of the wheel as 0.9 kilograms is shown in this graph, I believe. Yep. So if you look at the DVP 100, we can see that the mass of the wheel is 0.9 kilograms. So moving on, once we have all of these numbers specified for the application, we can run some numbers. The first thing we want to do is some preliminary intermediate numbers that we need to know, which is the wheel radius, which is obviously equals to the diameter of the wheel divided by 2. Circumference is obviously just 2 pi r, whatever the radius is. And the acceleration, the linear acceleration, is equal to the rated speed divided by the acceleration time, which if you run the number, it equals to 0.5 meters per second squared of linear acceleration. And once we get the linear acceleration, we can deduce the radial acceleration by dividing that by the circumference of the wheel itself, in which we get 10 radians per second squared of radial acceleration of the wheel. And if just as an extra, if you do want to know the radial acceleration of the motor itself, you can just multiply this by the reduction ratio, which gives us 200 radians per second squared of radial acceleration at the motor. This is usually not very important, but sometimes motors do have a limitation on how fast they can accelerate, so it might be good to know for future reference or depending on application specific requirements of the motor itself. And one other important number that we need to know is the rated speed of the motor, which we have calculated here to be the rated speed, rated linear speed divided by the circumference of the motor multiplied by the reduction ratio, which case we get 1,911 RPM from the motor, at the motor. So from this calculation, we do need these two numbers here of the angular acceleration and the motor's rated speed to be the two important numbers that we need to carry on farther into the next stage of the calculations. So moving on, the first thing we need to calculate is the vehicle inertia, which is the inertia of the total moving vehicle plus the drive wheels. And if you run this number here, we get a vehicle inertia of 37,522.5 kilograms centimeter squared. The next one we're going to calculate is the load inertia, which is the inertia of the AGV wheel plus the gearbox as reflected onto the motor, which is pretty much just this inertia multiplied by the reduction ratio plus the inertia of the gearbox itself, and which you get 94 kilograms centimeter squared. And this number, so this is the number that's actually reflected onto the motor itself, which we're going to use for future calculation. So we have our two inertia numbers for the system itself, and afterwards we calculate the load force, which is the force against friction needed to move the robot. This is where the rolling friction comes in. And if we calculate, this is calculated using just the gravity multiplied by some masses, multiplied by the number of wheels, plus the inertia of the wheel masses, multiplied by rolling friction, and we get a load force of 442 newtons. So this is pretty much the force needed to move the vehicle essentially across the ground, across the surface, across whatever surface that we are interacting with our polyurethane wheel. So afterwards, once we get the load force from the previous screen, we need to calculate the load torque, which is the torque against friction that's needed to move the vehicle by the motor itself. So, and that equates to the force multiplied by the diameter of the wheel, pretty much, multiplied by some efficiency and the reduction ratio. And the load torque we get as 1.38 Newton meters. So this 1.38 Newton meters is as seen by the motor, not as seen by the wheel. So this is the motor needs to generate 1.38 Newton meters of torque to move the vehicle, essentially. So just to move the vehicle, but in addition to just moving the vehicle across the friction of the surface itself, we also need to calculate how much torque is needed to accelerate the robot itself, which is calculated by the load inertia, which is the inertia of the entire vehicle, multiplied by the angular acceleration requirement of the motor, as we calculated earlier, which we have load inertia, we calculated last screen as 94.25 kilograms centimeters squared, multiplied by the angular acceleration of the motor itself that's needed, and in which case we get 1.885 Newton meters of acceleration torque that's needed. Then the total torque that's required to move the system, to move the robot itself, is going to be the torque needed to overcome friction plus the acceleration torque, which is multiplied by the torque safety factor, just to add a little bit of room overhead for safety here. Just in case we don't overload the system, in which case we get 4.899 Newton meters for the robot itself, but we have 2 drive wheels, so we divide that by 2 essentially, and we get 2.45 Newton meters of torque requirement per motor in order to run this robot at the speed and acceleration and load mass that we need to. So once we get this 2.45 Newton meter number from the motor, we can look up on this chart to see how much speed and torque we do need from the system. So if we refer back to our original slide, we did calculate that the motor needed to run at around 1,911 RPM to satisfy our speed requirement, with a rated torque of 2.45 Newton meters. In which case, if we look at the DVP 100, we can see that the 750 watt motor has a rated torque of 2.4 Newton meters with a peak torque of 7.16 Newton meters. So our torque requirement is 2.45, and this motor can output 2.4 Newton meters of rated torque. So this should be the correct motor size spec for this specific example, with a lot of torque headroom available as well for acceleration and emergency braking purposes. So once we selected that we wanted the DVP 100 diameter wheel size with a 750 watt motor with a 20:1 reduction ratio, as we've chosen, we can select the part number for the DVP product itself, and assuming that we want EtherCAT communication with this specific example. So here is the exact part number that we need to specify. So DVP-100 indicating 100 millimeters wheel diameter, plus an 80, which indicates a 750 watt motor size, plus a 20, which means a 2-stage 20:1 reduction ratio, a reducer in the middle, with EtherCAT communication. The 6 indicates a 16-bit encoder, 65,536, which is a standard DMM encoder, which is the only option for the DVP product, which, since the precision of the encoder is, significantly already higher than what's needed typically for AGV applications. And then we want the standard product with no options, assuming that the system operates at a flat surface, or maybe there's an external breaker, somewhat on the robot itself, so we don't need a brake, with no STO as well. So here is the overall part number that we should select for this mechanism, and of course we need 2 of these units to build the robot itself. So let's say if we were to size the system from the beginning, there's a couple things in terms of order of operations that the customer will need to know. The first thing you need to know is obviously the max load mass, which is the mass of the vehicle plus the maximum weight of the payload that it's going to be carrying. and you also need to know the max speed requirement, like how fast you want the robot to move, and the max acceleration, how fast you want the robot to accelerate, and the dimensional requirement to see how big of a wheel or how small of a wheel you can fit into your mechanical design of the system. Of course, these numbers are quite open, and there are a couple of free variables that you can select depending on your requirements for the robot itself, which includes the reduction ratio and the motor size and the number of drive wheels. So typically speaking, the load mass is going to be a pretty set in stone number. You're trying to have the robot carry a certain amount of payload for the application. So you're typically going to have the load mass pretty set in stone. And the dimensional requirement is typically pretty confirmed as well in the beginning in terms of how big your robot can be. So once you've selected the load mass and the dimensional requirement, every other parameter, honestly, is just quite freely selectable. You probably have a specific requirement for the speed, probably not for acceleration. You can probably set the acceleration to something that fits within the wheel diameter and the reduction ratio and the motor size, and of course your budget. So the acceleration typically is not so set in stone. So maybe you can leave this parameter open and play around with it a little bit in the calculator to see what works best in terms of overall balance of performance. So in order to simplify these calculations so you don't have to run it every single time, we've created a very simple Excel sheet that we will link in the this video description below, in which case you can just freely select all of these variables. In the green boxes and the red boxes will output all of the calculated parameters automatically. So you can sort of just freely play around with the numbers in the green boxes to see what number matches up, and you can sort of size the system very conveniently this way. And I will go through a quick example of what that looks like. So if I quickly open up the calculator here, you can see that these numbers are already loaded with the numbers that we've put into our example. But let's say, for example, if we wanted a total vehicle mass of 1,000 kilograms, we wanted to change the wheel diameter to maybe a 75 millimeter diameter wheel because we do have a lighter payload. Let's just change this to 750 kilograms actually, which is already quite heavy. And we want maybe a reduction ratio of maybe 15:1 reduction ratio. We have the gearbox inertia. Let's just keep that the same for now because, generally speaking, the reduction ratio doesn't change the gearbox inertia by that much. And the wheel mass will also keep as the same. Actually, the wheel mass might be a little bit different, even though it's not going to change the numbers a little bit. But if we look at the wheel mass of the 75 millimeter diameter DVP, we have a wheel mass of 0.7 kilograms, 75 millimeter diameter wheel. So we will put 0.7 kilograms here. Number of drive wheels, let's keep it at 2. Friction and the efficiency and the safety factor, we keep at the same. And let's just say this is a lighter vehicle, so maybe we want it to go a little bit faster. We want 50 meters per minute of speed. Maybe acceleration time, we want it a little bit faster, so maybe 0.75 seconds to reach the rated speed. And here we go in the red cells, they are updated immediately. So we have so in order to achieve this rated speed with this diameter wheel, we need a speed of 3,184 RPM from the motor. And these inertia and load torque numbers. So obviously, if you look at the very bottom here is the number that we're concerned with. The required torque per motor is 2.1 Newton meters. So if we look at the motor selection on this slide, so on page number 12, so if we look at the DVP 75 millimeter diameter wheel, we can see that the 400 watt motor option gives us a rated speed of 1.27 Newton meters. Now that's not quite enough to satisfy the 2 Newton meter requirement for the robot according to these numbers. But typically, I mean, the motor does have a peak torque of 3.82 Newton meters, which it can withstand for about roughly 3 seconds or so. So what we can do is we can check how much the acceleration torque is. The acceleration torque is 2 Newton meters, and the load torque to actually keep the system moving is only 0.7 Newton meters. So I can say that this motor, the 400 watt motor size, will probably work, especially since we do have that 1.5 x torque safety factor in place. So once, the acceleration torque, the required torque per motor, keep in mind, is the total torque needed to accelerate the system. But once the system is accelerated, we require very little acceleration torque anymore, and we only need the load torque to maintain the speed of 50 meters per minute. So this load torque typically is just the maintenance speed or the rated speed of the motor. So the load torque being 0.7 Newton meters, which is way lower than the motor's rated torque itself. So we can probably say that, again, this will work for the application. And if we also look at the acceleration time requirement, we can see that the acceleration time is only 0.75 seconds, but we already know that just by the characteristic of the motor itself, the motor can maintain the peak torque for roughly 3 seconds or so. So this 4 Newton meter of peak torque is easily covers 0.75 seconds of acceleration time that's needed for this system. So I would probably select the 75 millimeter 400 watt motor to be satisfactory for this application. But of course, if you do want the system to have more room of operational safety, what we can do is try to get this overall required torque to be around 1.3 Newton meters, which is going to involve some sacrifices. For example, we might have to increase the acceleration time down to 1 second or so, in order to get it down to about 1.7 Newton meters, which gets us closer to the rated safety margin torque of the 400 watt motor itself. So again, like all of these variables are very open, so you'll have to just kind of play around with them a little bit just to see what satisfies the constraints of the application itself and of the motor's performance. So yeah, that's pretty much all of the calculations that we need to do. Once, if you guys have any questions regarding the motor sizing or the drive sizing or even power sizing regarding power draw from the battery, feel free to contact us with any questions or concerns. But before I let you go with this video, I do also want to mention that we do have the DYN2X servo drive that is available for AGV and AMR applications. So this servo drive is a separate drive unit in and of itself. So you can pair the DMM motor together with a different gearbox to set up the overall system. So the DYN2X servo drive does have higher output. So if you do have a bigger capacity requirement, we do have a drive that goes up to 200 amps of peak current output. Whereas the DVP product line has a peak current output of about 50 amps or so. So the DYN2X will give you about 4 times more peak power output for your AGV and AMR applications. So yeah, that's the entire video of these calculations. And yeah, feel free to let us know if you have any questions. Thank you.